Section 16.3, the speed of a wave on a string. So the speed at which the wave moves to the right, which is shown here with this v, depends on how quickly one particle of the string is accelerated upward in response to the net pulling force, right? We can see at point 1, it's gone up, point 2 is in the process of going up, 3 is about to get yanked up, and 4 doesn't even know what's coming yet, but it will soon get yanked up. So how do we know how it's going to be accelerated? Well, it turns out it depends on two primary factors: on the tension of the string, so how taut it is, that if you pull it tighter, it will travel faster. And it will also depend on how heavy the string is, right? The linear density of it. If it's a really heavy string, it's not going to accelerate as much for the same given force. So we express that in this expression for the speed of a wave on a string. So note, as you write this equation down, I would add that label to keep it straight, that this is the speed of a wave on a string. And the speed is equal to the square root of the force, which is the tension force, divided by the linear density. And the linear density is sometimes given to you as a quantity, or other times you have to calculate it by noting that the linear density is this mass divided by length. So if they give you the total mass and the length of the string, you can calculate the linear density. And it's often easiest to calculate it before plugging it into this equation, just so you have it totally done and settled. So as we see, if you have a larger linear density, that's a more massive string relative to its length. And so it's going to be a slower speed, versus if you have a less mass in your string, then the wave is able to travel faster. Let's check out an example with this. So example 2, waves traveling on guitar strings. Super cool. Transverse waves can travel on each string of an electric guitar after the string is plucked. The length of each string between its two fixed ends is 0.628 meters, and the mass is 0.208 grams for the highest pitched E string and 3.32 grams for the lowest pitched E string. Each string is under a tension of 226 newtons. Find the speeds of the waves on the two strings. Right. So note we are trying to find V here, and it gives us the tension force. It also gives us the total length of the string and the mass for the two different strings. So this is a case where we can first solve for the linear density, and then we can plug it into that speed of a wave equation. Or we can even do it all together. That'll be just as equivalent. So using our speed of the wave equation, we should be able to find how the speed compares for the two strings, right? If it's the high E versus the low E. Okay, hopefully you are ready to see what's next. All right, so note we have our equation for the speed of a wave on a string, square root of the tension force divided by mass divided by length. And that's the same for both equations, for both the high E and the low E. The tension force is the same, the length is the same. The only thing that's different is the mass. And if you look at a guitar, you'll see this, that the high E string is very thin versus the low E string is thick. If you look at a bass guitar, the strings are even thicker. And that's shown in the calculations, right? As a result, the high E string, the speed of the wave, is 826 meters per second. Super fast. The low E is also fast, but it's about a quarter as fast, right? 207 meters per second. Not nearly as fast, but this is something we can actually calculate of how fast it will be. And as a side note for the musicians out there, since we know the speed of the wave is proportional to the frequency times the wavelength, and the wavelength is set by the length of the string, this is also how we can adjust the tuning of our guitar, right? If you twist the knob, you can increase the tension in the string. As you increase the tension, you'll increase the speed. If you increase the speed, you'll also increase the frequency. So you can bring your guitar to a higher pitch just by adjusting the tension. So that's a little bit of an aside, but I wanted to highlight it because it is very cool. All right, one more example for this section. Wave speed versus particle speed. Is the speed of a transverse wave on a string the same as the speed at which a particle on the string moves? So I want you to reflect on this before you go on. So go ahead and pause, and then you can see the result in just a moment. Right, so as we're thinking about this, note the particle on a transverse wave is moving up and down versus the wave itself is moving to the right. These are two very different motions, right? We could see them again with this animation of the particle is going up and down while the wave itself is moving rightward. So how do we describe the speed of each? Well, let's think first about the speed of the wave on a string. We just got an equation for that, right? That is the square root of the tension force divided by the linear density, mass per unit length. Okay, so as we look at that, notice those things are all fixed, right? We could adjust the tension, but as the wave moves, once you set the tension and the mass and the length, it'll just keep moving at that speed. What about for the particle? Well, for the particle, this is going to go back to the particle is moving up and down in simple harmonic motion. So we'd have to look at the speed of a particle in simple harmonic motion. And that would come from that sinusoidal equation that we got before. The amplitude times the angular frequency, that would be the maximum speed, but there's also this sine of omega t. What does this mean? This means that because there's this time dependence, this is not constant with time. This is changing as time passes. Right? And we could see that with this blue dot moving up and down, that at either end it briefly stops. It's very brief, but it does come to a stop, and it's moving fastest in the middle. So the speed of this particle is changing while the speed of the wave is staying constant. So this highlights that the particle and the wave have their own speeds, and you will need to keep those straight, that they are separate ideas. But if we're talking about the wave and it's on a string, we can go back to this equation, the square root of the tension divided by the linear density. All right, so this introduces the speed of a wave on a string. We're skipping 16.4. It's a mathematical description of a wave. You're welcome to check it out if you are interested, but it is one of the not required sections of our textbook. So with that, we will next up be heading to sound.